Well, welcome, Stephen. Thank you so much for coming on the podcast. Really appreciate it. We had a really awesome spaces that we did recently, and talking about some of the upcoming things that you've launched with Avalanche warp messaging. And more broadly, I've had a lot of fun just interviewing a lot of your colleagues with on the team and what you guys are building. So super excited to have this podcast. Thanks for coming on.
Oh yeah, thanks for having me. Yeah, no, I watched Patrick's podcast and I really enjoyed that whole vibe and your back and forth. So yeah, hoping to have a good time and looking forward to chat. Yeah.
Yeah, Patrick's awesome. Initially met both of you at the Avalanche conference. I believe it was the first one that you guys hosted in Spain. And I came up to you guys and was just blasting you guys with questions, trying to learn more about how Avalanche worked and the different virtual machines. And really glad we met there. So again, thank you for coming on. I would love to start the podcast, though, with a little bit of your background. I do find everybody's story unique. You were at Cornell. And kind of the birthplace of a lot of innovation that's happened in the crypto world. So I'd love to hear kind of your point of view of kind of the origin stories of Avalanche and how you got involved.
Yeah, for sure. So obviously Goon is going to be involved in this story for sure, right? And so I started at Cornell in 2016, focusing in CS. Ended up doing the standard track, going through whatever. Ended up getting particularly interested into distributed systems. So not necessarily consensus or anything that specific or even blockchain, but just in general distributed systems. So at the time, I thought that I was going to be really excited about like distributed computing and things like that. But what I ended up finding was consensus. And the thing that really kind of drew me into consensus was how logical the system is. So you can kind of like fully understand the end, the full process and prove its correctness. But it's also extremely difficult to reason about, right? So it's extremely complicated, but also extremely logical, which is just something that drew me into that. So I first actually met up with Goon when I was taking his operating systems class, and I really liked the operating systems class, but I also just really liked Goon's teaching style. He felt like a very like direct, manner of fact kind of guy, which I just enjoyed. That it was kind of like a breath of fresh air. And so after completing the operating systems class, I had that in the back of my head, and it turned out that he was actually teaching this class called Introduction to Cryptocurrencies and Smart Contracts, which that class, if you actually looked at the syllabus of it, it's a lot more low level than the kind of the title even says. You know, it goes into a lot of like, how does proof of work consensus, work, like dives into smart contracts, dives into like Merkle trees, of course, Ethereum, Bitcoin, and then also just like kind of consensus as a whole, and then like some cryptography things. And so that was super interesting to me, kind of like focusing in now a little bit more on these kind of more complex distributed systems and like all the different pieces being interacted with. And so then I went to do an internship. And right before I went to go on the internship, I asked Goon if I could do research with him, because obviously I was very interested in the area, taking a couple of his classes. And he said, yeah, like, let's start right now. And I was like, oh, sorry, I'm going to do this internship. Let's do it when we get back. And so on the way to to drive to like where I was going, which was New York City for the internship. It was an internship with Google, whatever. The Avalanche paper first dropped, and I was literally like reading it, and he had kind of like hinted that something interesting was going to be released in the space during the class. And I was like reading it, and I was just like so upset at myself, because I was like, oh, I could be working on this like right now, and instead I'm like going to do this internship. I did not turn the car around though, whatever. But anyway, so ended up doing the internship. After the end of that, going back into the fall semester of 2018 or so, started doing work with Goon on Avalanche. And so pretty much my first day, I just like went into his office and was like, cool, like really excited to work on this. Like, what do you think I should start on? And he asked me, so like, do you know Go or Rust? And I knew neither of those at the time. And so he said, all right, that's fine. So pick one, learn it, and write an Avalanche client in that language. And so I was like, all right, sounds interesting to say the least. And so ended up, after doing an extremely insufficient amount of research, for sure, on the the languages, I ended up picking Golang and started work on what is now Avalanche Go. So that was essentially the like Avalanche Go is my first Golang program, and it's pretty much my first foray into really deep diving into the whole crypto space. Yeah, so that's probably my very intro background story. Yeah.
That's an amazing story, and great place at being at the correct place at the correct time, and amazing that you got the opportunity to join Goon's class on cryptocurrencies.
Yeah, no, it was all very very lucky for me. I feel like the most important part of this process was not necessarily like my ability in programming or anything. It was like my refusal to like move on. Like I was definitely in the early days of working with Goon. I went into some meetings where like Ted, Goon, Kevin, and I were basically there, and they were doing this like research sync. And I must have been so annoying because like I remember very distinctly like them trying to explain stuff to me and me just being like, I don't get it. Like I don't understand. You're saying A implies B. Like no, this just doesn't make sense to me. I am very confident that I destroyed a couple meetings just due to like not letting them move on. Like I remember very explicitly one meeting, they were like, well, we can get back to this. And I was like, I don't understand how we're going to move on if I don't understand this, because this seems pretty important for like that. And so, so yeah, I ended up spending a lot of time just digging into the Avalanche paper and understanding stuff. I worked a lot with Ted, who Ted had done a lot of work with actual implementations of Avalanche. So Kevin was definitely more on like the theory side of like Snowball consensus, like proving convergence, safety, liveness, those things. Whereas Ted did a lot of the work on kind of making simulations and doing like throughput testing and things like that, and actually implementing the protocol. So ended up needing to bridge the gap in a couple places, but yeah, it was definitely very lucky for me to be there.
That's awesome. So after you started writing the Avalanche client in Go, what was the kind of timeline? How long did that take? And from there, how did it progress towards you joining the team full time afterwards?
That's actually a great question. So it progressed really rapidly. So at the time, the consensus paper had been out, but there was really no thought, and except for things probably in like Goon's mind on like what the actual like platform would end up becoming. This was before Ava Labs existed, so I'm sure that Goon had thought about starting Ava Labs, but I don't necessarily know what his thoughts were on that. But yeah, so we spent probably the first month or so just kind of like implementing the bare bones. Like you have to obviously implement the networking, you have to implement the random like message formats, and then of course the actual consensus protocol. And so that was probably not as long as you would think to get something just running, first pass. But there were a lot of like interesting kind of developments along the way, right? So at the beginning, the client was just implement Avalanche, right? And then it was like, all right, now we want to introduce this notion of like red nodes and like purple nodes. And like these guys don't actually know how to like communicate with. Now these end up turning into subnets, but like at the time it was like we want to like add this like kind of complexity, and I'm like, okay, never thought about that. Redesign, like redesign of the whole code base. And then I remember one time I ended up going into his office and he's like, hey Steven, like we had a talk today. How hard would it be to add like a linear chain to like your code? And I was like, I don't know, find out. And so like the very first pass of Snowman was like done in that like week of like trying to cram stuff together. And like, looking back, there's a bunch of really short iterations that happened where things were kind of getting proven out. Like what we ended up trying to introduce staking. And that is basically how like the P chain was very first created. And it's actually really interesting. If you look at the code base now, the code base is very separated between like Avalanche consensus and Snowman consensus, and they're very like separated entities. And at the time, that was definitely not the case. You had one DAG, and the actual whole consensus mechanism was just over the DAG itself. They weren't like separated at all, and that created some really interesting challenges. But one of the main reasons that it was kind of nixed and we didn't end up going down that route was because as you started to introduce subnets, it made less and less sense, because like the idea of maintaining this like global DAG for voting, but you're only voting over like these cuts, and like how do you define where these cuts are, and you have to like have all this verification to make sure you don't have like a spurious edge between two things. Anyway, we ended up kind of doing away with that and focusing more on like a more modular design. But yeah, just I think it probably makes sense to give a little high level before. So yeah, so the way that is it cool if we just kind of dive a little tangent here into consensus?
Yeah, let's do it. And Avalanche, I believe, was the first to implement a DAG structure on consensus. I know Sui now is kind of going that route, or at least the first big chain that I know of. Do you know of others?
So I think that the DAG-based stuff had been thrown around for a little while, but I think that there were always some issues. So I don't want to name too many names, like for whatever reasons, it just will sound too negative. But I don't necessarily know that Avalanche was the first DAG-based protocol, but I think it was the first one that really I felt good about. Let's leave it there.
Yeah. Okay. Sounds good. Yeah. Let's jump into Avalanche. Let's start with Snowball because I do think it's very unique. A lot of people have a hard time understanding it. I think it'd be awesome kind of hearing in your words how it works.
Yeah, so the key to all of Avalanche consensus, as you alluded to, is the Snowball consensus primitive. Essentially, all Snowball is doing is trying to decide on a single bit of information. So either yes or no, red or blue, or whatever you want to call it. So the way that the protocol works at its most like fundamental is pretty much just basic statistics. So if you imagine doing a census or like a sampling of a population, in general, the whole population isn't sampled, right? Like if you look at, say election results or whatever, like, I've never personally been asked, by any of these people who I voted for, right? But, you end up getting these polls that come out and say, oh, people are like leaning this way, that way, whatever, right? And the reason that works is just from basically simple statistics and probability is if you have a sufficiently large population, if you sample like, say, 10,000 people or 1,000 people out of like millions, you're actually going to get a statistically very accurate idea of the entire population, right? So that's the core idea behind the subsampling approach is, well, rather than knowing exactly how many people prefer red or prefer blue, what if we got a statistically significant measure to say, we are with high probability, at least 80% prefer red, right? If you know that, you don't necessarily need to continue on with asking more people if the protocol is just trying to figure out if you have 80% or more of red, right? So that's it's really doing at the end of the day. And the way that it does that is by just sampling a small constant size number of nodes in the network. Now, in order to actually create a consensus protocol out of it, you have to eventually have everyone decide on the same value, which is why you end up introducing this kind of like repeated sampling approach where you end up converting yourself to to the color that you think is the majority color, right? So if I sample people and I see 70% of the network is red, well, then I'm going to turn myself red. And just by performing that, if everyone in the network is performing that, you're going to very rapidly see that everyone is seeing that the network is red and they all turn red. So that is kind of the core of the slush primitive. So the slush primitive is actually just the first part of the snowball primitive, which is just this interactive kind of protocol of like repeated sampling. Sorry, do you have a question there?
And I love trying to get engineers to explain technical things in like non-technical manners. And I think you did a great job bringing it back to how, so it does this like statistical subsampling to try to find out what is the correct kind of state of information without having to ask everybody. By doing this, what is the benefits either from the user or directly to the network that benefits kind of in real world use cases?
Yeah, it's a very good question. So this whole side of the protocol is mainly focused around scaling out to have a large number of nodes. So if you look at other consensus protocols, I think that the one that I always name is Hot Stuff or maybe PBFT, things like that. So Hot Stuff is a consensus protocol, which the way that it works is it's an all it's like a broadcast base. So rather than subsampling, it communicates with everyone. And essentially the way it works is there's a leader, and that leader will send a message out to every node in the network and collect their responses, perform like maybe some aggregation if it's using like threshold cryptography. It doesn't necessarily have to do that. But anyways, and then it will send those messages back out to everyone and then move along. And then there's basically a rotation of the leaders. The problem with that is that the leader ends up communicating with everybody, right? And they have to then perform this additional work of like, maybe collating the messages and things like that, which ends up creating a large imbalance in the network. So all of the other nodes in the network are essentially only sending and receiving like one message in this example of like a fan out, fan back in. There's multiple iteration blurb. But the leader in this case is going to be dealing with messages from everybody. And so that means that a single node in the network has to deal with an O of n number of messages for a single decision. And that leader ends up becoming the bottleneck, right? Like you could say, well, rather than making everybody in the network do slightly more work, why don't we just have that one leader run a really beefy machine? Well, the problem is that if that leader fails, you have to select a new leader. And now all of a sudden, the new leader has to have that really beefy machine in order to maintain this. So what ends up happening is everyone in the network has to run a really beefy machine in order to like have larger and larger numbers of nodes in the network. This is very different with compared to something like Avalanche, where Avalanche, because you're only doing the subsampling and everyone is pretty much treated equally as far as the consensus sampling goes, there's no special node in the network that's doing like way more work than any other node at any given time. And so what that means is that, because you're basically doing a constant amount of work per node, regardless of the number of nodes. You can just keep scaling out more and more. And so that's essentially the key for like why you would pick Avalanche consensus over something else, is just that scaling out factor. Yeah.
And that helps being able to ultimately increase the number of full nodes, and by doing so you can effectively increase decentralization, and without kind of the performance degradations that other networks have because of this consensus and messaging overhead.
Yeah, exactly. Yeah, like exactly.
Very interesting.
Yeah, so
cool.
There's a lot of questions. I think there's a lot of weirdness around like what is actually a validator on like some of these networks, and so it gets it ends up being kind of like a hotly debated topic, even though I don't necessarily understand why. So touching a little bit on that, so in Avalanche, we typically consider validators as a full node that is participating in the consensus process and more explicitly being queried during the consensus process. So actually all nodes in the Avalanche network will perform queries, but only validators will receive queries. You know, they're basically the civil prevention of the network. In other protocols, you might have, I don't know, say like Cosmos, you have, 100 nodes and you have like delegation, and whatever 100 highest delegated nodes are like part of the protocol. Those are like the validators, I would say. In Ethereum, they term validators as deposits. And
yeah, that was always super strange to me and intellectually dishonest, which I do not appreciate about the Ethereum community.
So I don't think that that's necessarily fair. I don't know enough about ETH2.
Maybe it's a little bit harsh, but I think for me, like, I would love to see like a standard framework, and this is really what I've tried to like do a lot of my research on, because I wanted to essentially find like an apples to apples comparison. And the number of full nodes to me was like the best representation of like actually being able to quantify decentralization, and then the Nakamoto coefficient, because if you can achieve more than 1/3 stake, then you can start kind of messing with consensus. So to me, those were measurable, but the light clients, like, yes, I guess I get them on like ETH or deposits, but I don't know. I wouldn't count them as full nodes, and I get frustrated when people do.
I would love
to, if I'm wrong though, I would love to hear your point.
Well, I definitely agree. Like, I think things can be conflated. I don't want to say that it's intellectually dishonest, because I think that they had good reasons on why they did it, right? So my understanding of how ETH2 works is you basically have these committees that end up getting selected for the epoch. And I can tell you for sure it is a lot easier to select committees uniformly than from weighted distributions. And so it makes a lot of sense on why they would just say, a 32 ETH ends up, being part of the lottery to get selected for a committee. But I definitely wouldn't consider that something analogous to like
my word, not yours.
Yeah, I definitely wouldn't consider that analogous to like a validator, right? So I think if you look up validator statistics or like full node statistics on Ethereum, it's I don't know, like 7,000 full nodes or something run Ethereum, as far as a quick Google I could find. On Avalanche, we have 1,300 validator nodes and around like 1,700 other full nodes connected to the network. I think Bitcoin has the most full nodes out of everyone at like some like tens of thousands. But yeah, pretty cool.
And Avalanche also has a very high Nakamoto coefficient, which I think is extremely important. So that's impressive as well.
But yeah, anyways, it's all powered by the subsampling is kind of how we end up scaling out. I don't know if I'm just tying back into the consensus, a little bit, but
perfect.
But yeah, so continuing on a little bit with the Snowball algorithm. So we said that like, that's how the slush is done, is by this repeated subsampling. The additional part to that is you have to know when to finalize, right? And so we actually end up finalizing the consensus decision based off of the same statistical analysis. So essentially, once you have seen enough of the network, say like 90% or something of the network is all reporting this color, you know that if the process were to continue, everyone will eventually match that color, say red. And so you can just stop and finalize red at that point. So that's how consensus works on the bit level, on a single decision. And the kind of natural progression to that is, okay, well, how do you decide like multiple things, right? Like a blockchain, you're not deciding just like yes or no, right? So the actual natural progression of that is much more Snowman consensus than Avalanche. Avalanche is a lot more complicated than we probably should have jumped into the first paper, but Snowman is essentially how you would create a linear chain of this. And essentially the way you can do it is deciding this one bit of information like red or blue. You can use that to determine the bit of the next hash for the sequence of hashes, right? So if you decide, 256 bits, you've decided a full 32-byte hash, which is actually the hash of a block. And so if you just add in the requirement that this is a validated consensus, so essentially any decision that you're willing to vote on has to be provable to be a valid decision. Then essentially what you've done then is you have these blocks and you're just voting over the bits of this hash sequence, and you're just moving along. So, you decide something for this bit, decide something for that bit, you move along, and you end up deciding a full block, and you've moved along the whole chain. That sounds super slow when you say it that way, because you're like, oh my God, you're performing consensus, which is expensive, for every single bit in the whole series. But an important kind of addition for Snowman to work efficiently is pipelining. So you're not voting over just one bit at a time. You're actually voting over a full prefix of bits. And so what ends up happening is, in the normal case, you're ending up just basically performing the work of a single Snowball query for however many blocks you have undecided. And so that ends up making the Snowball, like the Snowball transition into Snowman, very efficient, assuming there are no conflicts. If there are a lot of conflicts, then you have to do a logarithmic number, because it's bitwise, to decide which block to actually end up accepting. And then this ends up kind of going into like Snowman ++ territory with like designated block proposers or producers. But yeah, so that's kind of the key of pretty much the whole Avalanche network, with the sole exception of the X chain. So almost every chain in the network runs Snowman ++ and Snowman consensus. The only exception to that is actually the X chain, which uses the full DAG-based Avalanche specification. So,
gotcha. Yeah. How does so, and maybe if I could just re-summarize, what you have created and the team has created is kind of statistically being able, like with a high degree of confidence, kind of based off statistics, you don't have to pull every single node in the network, and you have a high degree of saying that the network is agreeing upon a certain transition or execution on the network. And what that allows for is a large number of full nodes that has constant work, where other nodes are not constant. And so it requires much larger nodes. So you can have a higher degree of one, or a higher probability, I guess, of censorship resistance and a large degree of full nodes in the network. And then with the consent, sorry, go ahead.
Yeah, no, I wanted to agree on that, but also maybe pull the veil back a little bit. We aren't necessarily doing all of this solely to get the like as many nodes as possible, right? So a key part that is also important to Avalanche is the fact that it confirms blocks and transactions extremely quickly with low latencies, right? And so if you actually look
Yes.
at proof of work, proof of work is pretty much the most efficient thing you could ever imagine as far as a verifier side, right? Definitely not on the producer side, but on the verifier side, really all you have to do in order to perform consensus is just gossip these blocks around the network, right? And so they have a very similar communication overhead to our, sampling, but it's actually even smaller because all they're doing is just pushing the block once. They never have this repeated thing. They're basically only doing it once. And then they're just verifying hashes and just following whichever one has the most proof of work, right? So essentially what Avalanche is trying to do is take the nice parts of that, which is, extremely low overhead on a node, but combine that with something more traditional, which comes out of voting-based protocols, which is the low latencies. So if you look at Bitcoin, Ethereum pre-merge, the confirmation latencies were, on the order of minutes, sometimes even higher. Like the Bitcoin white paper, I think recommends, is it 6 block confirmations, which is like an hour, I think.
Yeah.
So
An
that's,
hour.
yeah. So
Yeah.
I don't think anyone's using that now. I think most exchanges, which is generally the rule of thumb for confirmation requirements, is probably way lower than that, probably like 2 or 3 confirmations. But even that, it's like, really slow. But Avalanche confirms this whole process in generally around like a second, maybe like a second and a half once the node actually starts polling, which means the end-to-end latency for a transaction that is submitted into Avalanche is probably like, I don't know, maybe like 2 seconds or so, which is usable, right? The whole joke about Bitcoin with like, you order your coffee and then it gets cold as it's waiting for the confirmation to go through. Like you can definitely order a coffee with the Avalanche latencies. So that's really
That's important.
that's really the whole importance, is being able to order your coffee and also having a large number of nodes in the network. So yeah.
Perfect. Well, I appreciate you walking us through that. I do think, it is misunderstood. I'd say more broadly. I think like the early days of the internet, unfortunately, the space is just technical. A lot of these kind of innovations come through these technical breakthroughs. And so I just wanted to talk about really the thing that powers the Avalanche ecosystem. So I appreciate you breaking that down.
Yeah.
Maybe shifting gears a little bit. You and I are big fans of virtual machines and all the different kind of combinations of what they can do. Can you talk about one, kind of Avalanche's flexibility in its design to allow subnets to have custom virtual machines, and then maybe some virtual machines that you're excited about for this upcoming year?
Yeah, for sure. So going back to our conversation earlier where we have like the purple nodes and the blue nodes and the red nodes, right? So what we ended up kind of falling down was this route of subnets. And so subnets, you register on what we call the P chain, which ends up resulting in you being able to allocate validators to your subnet. And well, what do they validate? They validate a blockchain of the subnets kind of choosing, right? So it's really interesting kind of even talking about like what is necessarily a blockchain. So a blockchain in the traditional sense is just essentially a hash chain up the, making sure that you record all the previous states, and then you have maybe some like state machine that executes over them. So I was, when I was first implementing the client, I was wholly inconfident, or I had no confidence in myself to actually be able to write a universally nice virtual machine that everyone would just see and be like, oh, this is perfect. And so, and I think that Goon definitely echoed that kind of sentiment of like, yeah, no, like we're never going to come up with, the perfect virtual machine, right? And so the idea was to basically allow users to register plugins with the Avalanche Go binary to define that state machine that executes over these blocks to then produce whatever the blockchain is. So it actually extends a little bit more than that as well. We don't necessarily need to have blocks anymore for a VM. You can define basically just your own like networking interface. So you could define a plugin that just latches into Avalanche's P2P network and send messages. You don't necessarily have to be performing consensus, but the traditional sense, you typically have a blockchain, and so a VM is just defining what the blocks are, so like how they're serialized, like what is contained inside of them, and also you're defining what the disk state looks like. What is the state of the virtual machine, or say like the current state of the blockchain, and so that's pretty much it. Essentially, the way that VMs work is they all talk over this plugin interface, which actually just uses gRPC, so Google's like protobuf based RPC protocol, there's a relatively extensive and very flexible interface that Avalanche Go provides for VM developers. And so that means that these VMs can be implemented in pretty much any language that supports gRPC would be useful, but not necessarily required, because like you could technically implement it by yourself. But that includes things like Java, Rust, Go, C++, you name it. There's I think like Node.js, like you could probably implement a VM in Node if you wanted to. So it's an extremely flexible interface. And pretty much all you have to do to get started is define things like verify this block, accept this block, reject this block, build a block. Those are pretty much the main things required to get off the ground and running. And then there's a bunch of additional things as you peel back the curtain even more that you can play with. But that's yeah.
The one thing that you touched, well, there's a couple things that you touched upon, but the first one I think that is interesting is being able to customize the networking layer. Have you seen any subnets start to play around with that?
So I think that we've definitely seen subnets utilize this interface. The most common thing is to hook up a mempool to it. So that's like the most kind of natural progression, right? Like it helps out with like building blocks and various things like that. The subnet EVM also uses this to support state syncing. So that's actually a large functionality that the subnet EVM provides using this. I'm really excited for someone to go really off the wall using this. So some of the ideas that we've had are things like, implementing a DHT using the P2P network here, right? So rather than, implementing this like BFT consensus protocol, what you could use this for is, just a much more standard like distributed hash table for managing data. Doesn't even need to necessarily be BFT. Would be really cool. It's just an example of utilizing the Avalanche P2P network for additional interesting things. So I think that's like something I would be really interested in seeing someone kind of pick up. I don't necessarily know that anyone has picked up something like that yet, but yeah, it's pretty flexible. So yeah.
Yeah, that's what I've always been super impressed by the design of Avalanche when I met you and the team was how flexible it ultimately was. Being able to customize the networking stack, I think I'm excited as well to see different teams kind of play around with this and see what they try to do. On the virtual machine side, so the C chain today is a modified version of the EVM, which is a serialized virtual machine. And are you, I guess, for you and the team, I know there's the EVM++, and what other virtual machines what enhancements, I guess, are you going to make to that like specific virtual machine? What would you love to see people experiment with on the virtual machine sides on individual subnets?
So, this is a great question. So I'm going to start with the second part first, because I think that's the most exciting just to me to talk about, which is what people should be experimenting with. So the really nice thing about Avalanche, right, is you can like deploy whatever VM you want, and if it sucks, it breaks, it doesn't necessarily like do anything, right? Like you don't have to have some like huge investment necessarily to play around with something and launch it, right? And so as far as the subnet EVM goes, or just EVM in general, the most interesting design space for me is around state management. So I think there's a really great talk that Peter Schlage gave about how like read amplification and write amplification ends up happening through like the Merkle tree used by the EVM. And so a really interesting thing is you don't necessarily have to worry about any of this if you have a fixed state size, right? So the way that Ethereum works is you pay some money for gas to like say deploy a smart contract or allocate storage, but that storage can pretty much just stay there forever, right? You don't have to like necessarily continue to pay more and more. And so there's a lot of really interesting ways on how you can implement like fixed state size virtual machines. And I think it would be surprisingly easy to implement some of those inside of the subnet EVM to play around with that. So a good example of that may be, say you have some token, right? And you use that token for gas, but you could also use that token as just a fixed deposit. So say we wouldn't probably do this, but like say like you wanted to say have one Avox allocate 8 megabytes or something, or say 1 megabyte to make the math easier. If you did that because Avox is hard capped, you know that there's never going to be more than 720 million Avox. You have already hard capped the max storage state size of the VM to be 720 million megabytes. That's a lot. So you'd probably want to reduce that a bit to say like, allocate less than a megabyte per Avox or something. But if you said like 1 byte per Avox, then I think you end up getting like a 720 meg capped state size, right? Which is really fascinating, right? Like that's probably going to be way too much money in practice, but that's just an example of a not super complicated way to introduce a fixed state size into a virtual machine. Now, there's a lot more interesting ways you can do like state rent and things like that. And, maybe you have like an EIP 1559 style, which is basically dynamic usage targeting for like your state size. So, if you go above the target state size, then you increase the rent price and things like that. And there's a lot of interesting challenges that comes along with these protocols, but like that is something that if implemented, the performance of that VM could just be absolutely ridiculous. The whole reason why BC Chain and Ethereum and things like that, the reason that they're there's 2 reasons. But the first reason why they don't do this is because if they just increase the gas usage, the network wouldn't actually tip over, right? And you've seen this with things like BSC, where they have a much higher gas usage over time. And the problem isn't the current time, it's in the future, you're going to have huge disks and you're going to be extremely slow and clunky, and you're not really going to be able to move things along. But if you had a fixed storage state size, that's actually not a problem. You've bounded how much work you're going to have to do. And so you can process significantly more transactions now and not worry about in the future needing to like pull it back because it's too slow. There's still the concern around like people needing to sync the chain. So they have to be able to process faster than new blocks are coming in. So you still have to kind of gauge that out. You can't necessarily run it as hot as humanly possible, but you can run it much hotter or faster than currently people are running it that are doing it responsibly. So that is, yeah, a very interesting design space that I would love people to play around with. Going into what the EVM is, it's actually probably mainly targeting around the same thing, which is state storage, but not necessarily in a fixed state size way. So there's two different kind of levers to pull, right? And the first lever is, well, let's just cap how much state you use, and then you can go from there. The other lever is saying, well, how efficiently can you manage that state, right? And if you're managing state extremely efficiently, then you can have a higher state cap, which is more usable, and still be able to kind of interact with it. So I think a lot of the work internally around the EVM++ right now is focusing on the state side, but there's also some kind of interesting ideas floating around about how you might extend the EVM, keeping it to be compatible, bytecode compatible with Ethereum, so you can still kind of like deploy your contracts, but while potentially adding in some new additional features. So a lot of those new features are still kind of up in the air, but the state side is really pretty concrete and pretty cool. So yeah.
I love asking people, what do you think is the kind of like biggest bottleneck in blockchains? I've had different answers. Some say it's the virtual machines. Some say it's the amount of data that is available. Some say it is storage. In your opinion, what do you think, if we truly want to scale blockchains, what is the biggest hurdle to kind of hitting that large amount of like daily active users from the technical side?
Okay, yeah. So from my viewpoint, I think that current blockchain networks probably tried to do too much, honestly. So if you look at things like Geth or like the Bitcoin Core, these nodes do a million things, of which they probably don't need to do that. So an example of that is syncing the full historical state of the chain, right? Is it actually important for nodes to be able to join this P2P network and sync the historical state of the chain at a whim and support, querying the balance at any state of the network at any given point in time in the past, decade or however long this thing has been running? Probably not. I would say that's feature creep to the max and should probably not be part of most blockchain node implementations. I think it's super important to be able to look at and like still audit the state, because that's the whole point of blockchain, is right, you have this like auditable ledger going back forever, but it's not really up to everyone in the network to do this, right? And so I think that current blockchain clients should probably delete around 90% of their tech debt and say, you know what, like, we're running a client. All this client does is moves blocks along. It keeps adding new blocks to the ledger and fully validates, right? So from that perspective, I don't necessarily think that clients should keep historical chain state. I think they should pretty much just keep whatever chain state they need in order to be safe and continue the protocol along. And when you say it kind of like that, and like, all right, that's all we're doing on the client side, pretty much all that matters at that point is managing the validation of new state and the lookups into the current state, right? So that means that there is the virtual machine actually executing instructions, and then there is the state management for the current state. If you look at VMs right now, pretty much the main problem with VMs is that they pretty much ignored the state management side. So I think that there's a lot of VMs coming out now. I think Move does this pretty well around separating out different parts so that it's actually easier and more efficient to manage the current state of the network. And then there is a number of data structures that people are working on or that existed and weren't being used for managing the state. So I think that the core bottleneck is generally the state, but what ends up happening is the VM design can sometimes cause the state to need to be less efficient than is necessarily optimal. So it's really both of those two things, in my opinion, that need to be optimized for. And yeah, so that's kind of our focus is implementing some high performance state engines right now, and then plugging that into some high performance VMs. So we have a really cool demo that we're working on, but I don't necessarily know when it's gonna come out. But yeah,
it's okay. You can share the alpha here.
That's about it. That's about all the alpha there is to share. Like
that's it. That's
shocking.
Okay, cool.
Shocking. We're working on high performance state management and high performance VMs. Shocking, right? Cool. But yeah, I mean, people throw out like TPS a lot, and like you can get to stupidly high TPS numbers if you bound the state size and then you perform efficient like state trends. So like if you have a well-designed VM and a well-designed state model, you can get absolutely ludicrous throughput numbers. Like I think Solana is probably showing at least some of that.
And what's ludicrous?
Like what do you want it to be? Like, like at some level it ends up being how big do you want your machines to get, right? Like if you want it to be verified on a beefy laptop, you can probably get at least tens of thousands of TPS for sure, performing say like something along the lines of like transfers, things like that. I don't want to go down like the realm of
we don't have to.
Yeah, the realm of different TPS games and
transfers. Yeah. All good. Well, I definitely appreciate us kind of getting into Snowball and deep diving the algorithm. Appreciate your thoughts on the different virtual machines, but I would like to talk about the Avalanche warp messaging, just because that's something that you guys launched recently. So please, maybe just in your words, kind of describe it and why it's kind of so important for the Avalanche ecosystem.
Yeah. So having all these VMs running all their cool designs is a really nice thing to have for the Avalanche network, but there's really no point in there being a network if those VMs can't communicate with each other, right? So it's always been a goal for the Avalanche network to be able to communicate cross subnet. And so AWM or like warp messaging added that capability in. It's really not too difficult to add such a thing in. Like we've kind of known how we wanted to do it for a real long time, and really the crux of it is making sure that you can perform these verifications efficiently. And by efficiently, it generally means without the primary network or every node in the network performing work. And also for the individual subnets to be able to handle that efficiently. So that's really the thing that was kind of blocking for us to end up like really deciding on how we wanted to do this. And what we ended up deciding on doing is creating something that is pretty upgradable, right? So not only is it just like some structure and we say this is it and it'll always be this, we wanted to support upgrades and future like additions to the protocol, and get like a reasonable first pass in for efficiency. So the way that the warp messaging works is utilizing the P chain. So the P chain for the Avalanche network is really the heart of the network. It manages all of the validator sets of all of the subnets and defines all the VMs for all of the chains on those subnets. And so the way that warp messaging works is you may send a transaction on some chain, and the validators will end up attesting to that event, whatever it may be. And then a recipient chain can receive that message, verify that attestation based off of the state of the P chain, and then execute that message on the destination chain. So the way that that attestation is currently formed is based off of BLS multi-signatures or aggregated BLS signatures. That is necessarily, that's how it currently works, but can be upgraded and changed as more efficient or more, say, like future-proof things come out. So I know that there's a talk around like quantum security around BLS, and sure, that's a concern, and so we definitely didn't want to just like marry ourselves to BLS forever. But currently, it's definitely suits all of our needs. So that's the core of how warp messaging works. Is just this simple like send, attest, and then receive. But how we actually got to that point is a lot more kind of complicated. So it actually goes all the way back to the introduction of Snowman++, which is when we actually created this dependency of the chains onto the P chain. So the way that Snowman++ works is it ends up defining proposer lists for blocks for their respective chain. And in order to do that, it has this dependency on the validator set of the P chain at that point in time. And so you end up basically tracking the validator set changes and incorporating that into your chain through P chain height references. And by doing that, we end up registering not just the validator set of your current chain, which is all Snowman++ used it for, but actually the validator sets of all other chains in the Avalanche network. And so by just extending this to basically be shown over the VM interface, you can actually directly reference the height of the P chain provided in the proposer VM block and reference the validator sets of any subnet on the network. And that's how that attestation is actually performed. So a lot of the work around this like kind of messaging primitive has really been focusing on P chain extensions and support and efficiency. And so if you look back over, all of the prior network upgrades, it might not have been super clear at the time, but this is kind of what we had always been pushing towards, is kind of like centering the P chain in this like network for message passing. There's a lot more left to do with the message passing though. So the way that warp messaging works is kind of inherently as it's as efficient as possible because it doesn't touch the primary network. But by doing that, it also kind of inherently introduces some non-reliability of the messaging, right? So one thing that I'm really excited on doing is kind of introducing different flavors of this messaging. So an example of something really cool that you can do is if you wanted to have this message be delivered reliably, guaranteed, right? Well, you can again use, say, the primary network to use that as a kind of global timestamping service, so that the sender chain is guaranteed to know that the receiver chain has actually received that message. And so that's an extension that I'm kind of looking forward to pushing along, but also just kind of seeing protocols come out as a part of the warp messaging. So warp messaging is very flexible. It's basically just an envelope of like attested data from a chain. And so that data can be arbitrary. It can kick off, turn complete communication or turn complete execution upon delivery, and pretty much anything. And so I'm really excited to see some of the usages of the warp messaging, especially coming around in things like the EVM, because I think that'll probably be the main focal point when that comes out. But yeah,
definitely. Subnet to subnet communication is massive, and being able to kind of natively do that in the Avalanche ecosystem, I think is going to be something that's helpful for the entire ecosystem and hopefully loved by users to be able to pretty easily go from subnet to subnet. One thing that we've seen, I would say, in the last couple of years has been different hacks or different bridging communications where they have kind of fallen down. How would, in your words, would you like explain to non-technical people how the Avalanche ecosystem and team is thinking about security from subnet to subnet more broadly?
Yeah, so I typically break these down into like two separate concerns. So the first concern or like reason that exploits can happen is caused by just incorrect implementations of the protocol, right? So it might be that, you know, as an example, you might have like some smart contract based bridge with just a pure multisig, and that bridge is fine. You know, the multisig isn't corrupted, but there's some exploit in the smart contract that ends up happening where you can drain stuff out, right? So that kind of a exploit is pretty hard to just fix in any general messaging protocol, but the hope is that you can make it as clean as possible to implement and as simple to implement that it's hard to get it wrong, right? So you want basically something that's extremely simple from a UX side and very easy to understand from like the dev side, so that you minimize kind of the attack surface there. The other situation where bridges could fail is if the actual kind of bridge owner fails, right? So generally you have these like multi-sig bridges, right? And like if you have, say, like a 7 out of 9 multi-sig, well, if 7 of those people don't manage their private keys correctly, then they can just arbitrarily take anything out of the bridge, right? So that is definitely something you can just solve immediately using something like AWM. And the reason for that is because using warp messaging, you don't actually have what are traditionally called like the relayers of the bridge, right? Those relayers, there might be relayers in order to actually pass the message, but they aren't actually involved in any of the security of the message itself, right? So there's no one necessarily to attack other than the validators of the subnet themselves, which is just the security of your chain, right? So those are kind of like the two areas. And so the way that warp messaging is set up, we just cut out the entire, concern around that bridge operator failing to do their duty. And then the goal then is to make the actual implementation of the bridge as kind of simple and as easy to use as possible. And so definitely look forward to seeing some really cool, crazy protocols coming out for warp messaging that will make bridges extremely easy to implement. So that's definitely a major focus right now for us to incorporate into the subnet EVM.
Yeah, I think bridges today kind of have a scary connotation. I think definitely over time that will fade, especially as better implementations get developed. But they are, I would say, even I would say they're still difficult to understand. One maybe other kind of point of reference here, a lot of people a good amount of people kind of compare Avalanche to the Cosmos ecosystem, and the Cosmos ecosystem also has IBC that allows bridging between different Cosmos zones. How would you, maybe to kind of wrap up Avalanche warp messaging, how would you describe like the differences or comparisons to the implementation that Cosmos has?
Yeah, so IBC is focused on Well, so the way that IBC works is essentially running a light client of your sister chain or whatever, right? So light clients are generally, well, they're much more efficient to run than full clients, but they're not generally free by any means. So if you actually look for how a light client is implemented in something like Cosmos, you have to validate all of the signatures going from like block to block or validator set to validator set changes. And you have to basically keep that up to date. So if I am some zone on Cosmos, I have to be keeping up to date with the block headers and verifying all of the signatures of all of the zones that I am interacting with, right? So that is super general and super flexible, which is nice. But the problem is that you have this kind of like n squared complexity where all of a sudden everyone's verifying headers of everybody else as you're trying to like pass messages around. So one of the really cool things that I like about the warp messaging is how it uses the P chain as kind of this like global validator set service, right? So the assumption is that, well, validator sets, they're probably not going to be like changing some huge amount, right? Like you're not going to just see like rapid changes. And so why don't we set up kind of a global ledger that keeps track of everything for everybody? And now rather than verifying headers of all these different n squared chains, you can just keep track with the P chain, keep that up to date on all the validator sets of all of the subnets, and then use that information to then communicate. So I would say that the actual guarantees at the end of the day are probably pretty similar because, you know, if on Cosmos you're keeping up with the headers, you do know their validator set, and so you can then interact and like take that message from them based off of their validator set reliably. But this is just, in my opinion, a more efficient way of performing that for a much larger number of chains. Yeah.
Makes sense. And so in the Cosmos example, because it is n squared, that either affects the number of nodes you can run, or does it just make it so the light clients have to be larger hardware, or both?
Yeah. So so the n here is actually the number of zones. So like if I'm a zone, then I have to be running light clients for all the other chains that I'm accepting messages from. So that means that, you know, if there's a click of like 5 people, then all of a sudden everyone has 4 connections, which is where you get that like n squared interaction from. But yeah, so actually an interesting point on that though is, and this is maybe diving outside of my area of Cosmos, so maybe I shouldn't talk, but I believe that the light client verifications are a function of the number of validators on that chain, unless they use threshold crypto, which I don't think they do. And so that means that, you know, if you have more and more validators, like the actual communication can actually start getting a lot more expensive. And of course, that is something that as a chain, you have to keep up to date as it moves along. And so that ends up taking away from the actual operations that your chain can do of its own interesting kind of operation, because now you're validating all the headers of all the other kind of chains that you're doing. So, yeah.
Very interesting. Well, yeah, definitely appreciate the deep dive. I think as kind of people become more kind of have greater depth of knowledge in these specific areas that today I would say largely they feel uncomfortable, they'll over time feel better about moving their assets from different chains. So appreciate the clarity there. Yeah. We've definitely touched upon a lot kind of in the Avalanche ecosystem with Snowball, different virtual machines, what you guys are doing in terms of the EVM++, also the new Avalanche messaging between different subnets. I guess kind of wrapping up the podcast, what things, I mean, a lot has happened in 2021, kind of crazy year. A lot has happened in 2022. What are you specifically looking forward to for this upcoming year in 2023, or things that you would just like to see get built more broadly to get user adoption?
Yeah. So I when when this kind of comes up, I have two things that immediately jump into my mind. So the first is moon math stuff. So there's a lot of really interesting cryptography advancements being made pretty much every day. So I think like today there was a paper pushed out about BLS threshold, or that could support like BLS threshold generation and like cubic complexity for like a threshold cryptography using BLS, which I find really fascinating for like various things, including like VRFs and things. So I'm really excited about just the general advancement of cryptography, and that's a big reason why we're pushing for the Rust SDK. The Rust SDK, I'm hoping, is going to kind of allow the usage of this kind of like more exploratory cryptography to explode, because a lot of the interesting cryptography advancements are happening in the Rust ecosystem right now. So I'm really excited for kind of like the Rust SDK to take off and see a lot more of just like crazy new VMs that like I never knew were possible. So I think pretty much like a week ago or something, some random person threw out that they were working on like a zero knowledge VM that like using bulletproofs in Rust SDK. And I was just like, that's cool. Like I'm in on that, very, very exciting stuff. So that is an area that I'm really excited on. The other area is just general SDK development for more high performant chains. So currently, I would say it's not super easy to deploy a custom VM from scratch unless you are a couple people in the world right now. So the XSVM, the cross subnet VM, in case people didn't know what that actually stood for, the XSVM took me probably a couple days to implement from scratch, but I would not expect that from just following our online documentation, right? So I think that we have a long way to go on both improving just the docs of like how to actually build out a VM, but also for developing out a lot more of like composable VM components that people will find really interesting. So I definitely don't want people to be implementing their own mempool or implementing their own, Merkle tree storage, or, implementing how like block state is passed from parent to child in the VM. Like these are all things that can be pulled out and modularized and then just kind of reused as components. So I think that really 2023, I'm hoping, is going to be kind of the year of pushing out VM development and making it a lot more kind of mainstream with just kind of how usable it is. So I'm hoping that the development flows out from kind of the Avalanche core stack, which is like, say, something like Avalanche Go, into things like the VM implementations. So I have no idea how happy I would be if someone just randomly said like, oh, hey, I took like the XSVM and forked it and added in some like random like VM scripting thing and like added in some like state, or like, that would just be like, oh, cool. Like, let's dig into this. Let's see how it works. Like, yeah, that's my hope for 2023 for sure. So yeah.
Perfect. More and cooler cryptography and modularizing and better VMs. I love it.
Yeah.
Perfect. Well, how to, I guess, people that want to learn more about the Avalanche ecosystem, if they have questions on any of this cool stuff or ultimately want to build new virtual machines, where would you point them to?
Yeah, so I think the two areas that I would definitely point people to is either the Discord. So we have, I think if you just go to like chat.avox.network, I think it'll immediately link you to our Discord. And that's definitely the first place that I would stop at for asking any technical questions. If you're just getting started trying to play around with like what Avalanche is and just kind of learn about it, the docs is probably a good first place to go, but you'll probably end up needing to then go to the Discord to ask any really like low level meaty questions. So there's docs.avoxa.network and then also chat.avoxa.network are probably the two major places to go if you're looking to do VM development. I also am trying to like pay attention to like things like Twitter now. I'm definitely not a native Twitterer or Twitter tweeter or whatever. But I try to pay attention to that. So if anyone has any particularly interesting questions, either feel free to DM me there or just post or something and at me. Yeah.
Perfect. Well, thank you again for coming on the podcast. I really was looking forward to it. And always my favorite conversations are with the technical people that can go extremely deep and communicate those into normal speak. So I really appreciate you coming on, sharing all the special sauce that makes Avalanche. And look forward to 2023 as well. So thank you.
Thanks very much, Logan.